Good morning. So this is the report on the forced convection experiment, where it was an investigation of the cooling of aluminum and concrete cylinders under forced convection. This is Team 4. I am Molly Pavey, and I am joined by Christina Luong, Anna Mangus, and Nicole Martin. So for background, forced convection describes the form of heat transfer between a body and its surroundings that is caused by the bulk motion of fluid flowing past the body. So in the diagram on the right, you can see that that's in contrast with natural convection, where in natural convection, there is natural mixing caused by the change in density as the surrounding fluid will change temperature. In forced convection, the fluid is forced to flow, and what this does is it increases the rate at which heat transfer occurs because there is far more motion occurring past the object. So forced convection is typically explained using Fourier's laws. It is derived off of Newton's laws of cooling in addition with a kinetic theory. This basically agrees that heat convection is driven by a temperature gradient between an object and its surroundings, and the vibration of atoms, which is the kinetic theory, then transfers heat to the adjacent atoms. This can either be from heat leaving the body to cooler surroundings or an object taking in heat from a warmer surroundings. So convection is focused on the body to the surroundings. This is in contrast to the second form of heat transfer in a body, which is throughout the body, known as conduction. The importance of understanding this is in a real-world context, you often need to understand how quickly heat will transfer and at what temperature range you can expect an object to be in a particular time span. This is important as many materials will have particular temperature ranges where they are most effective and particularly where they are most safe in an industrial context. So in this experiment, our main goal was to then experimentally determine what the heat transfer coefficient was for varying materials. So we were performing experiments where we were recording the temperature change of an object placed under forced convection. And one of the things that we were looking for is whether or not a temperature gradient occurred within the solid. So this basically describes if the temperature of the surface is similar to the temperature at the core, or if the core will constantly remain at a higher temperature because there is some conductive resistance inside the object. Why this matters is it impacts which types of analytical methods can be applied. In the event that there is very little temperature gradient within the solid, a lumped capacity method can be applied. The lumped capacity method then depends on the Biot number, which is a dimensionless number to describe what the relationship is between both the geometry of an object and the relationship between the convective coefficient and the conductive coefficient. In the event that the lumped capacity method cannot be used, in that case, then there are reference charts that exist. Each chart pairs with a particular geometry and cares about, on the x-axis, the time, on the y-axis, the temperature, and then on the chart, you read off values that care about the conductive coefficients and the convective coefficient. In this experiment, we assumed that the only cooling occurring for the solid is due to the surrounding air flowing past, and there was no loss of heat on the top or bottom surfaces.
So for materials, methods, and safety, to start with our materials, we used a cement cylinder, an unknown metal cylinder with thermocouples inserted at the middle and at the edge, an oven to heat the objects to the desired temperature, a wind box consisting of an air blower, a stand, and a thermocouple to measure the ambient air, as well as a ruler to measure the diameter of the cylinders. For the steps that were taken for this experiment, first, the cylinders were heated in an oven to about 150 to 160 degrees Fahrenheit. Then, while the cylinder was heated, the stand was adjusted to the desired height and the wind speed was measured. Next, the cylinder was removed with heat-resistant gloves and placed on the stand in the wind tunnel. Following, the inner and outer temperatures of the cylinder was measured every 30 seconds. Once the temperature dropped about 1 degree every minute, the measuring was ceased. Finally, the diameter of the cylinder was measured. And then this was repeated with the other cylinder. The safety measures that were taken were hot pads were to be used to handle the heated elements of the lab, such as the cylinders when they were coming out of the oven. And if a burn were to occur, lukewarm water would be applied to the affected area and the proper personnel would be notified.
So this is the temperature profile that was found for the metal cylinder over time. And as you can see, the surface and internal temperature were basically the same over the course of time. So it shows that the temperatures at the surface and center were nearly identical. And because of this, we can assume that there's negligible internal resistance and treat the entire object to be the same temperature. Because of this, we were able to use the lumped capacity method, and from this we found that H was 45.74 watts per meter squared Kelvin, and we calculated the Biot number to be 0.0034, which is less than 0.1, and this confirms our usage of the lumped capacity method. Now here's the temperature profile for the concrete cylinder over time, and here the surface temperature changes at a different rate than the internal temperature. And so because of this, we cannot assume that the temperature of the entire object is the same during our calculations. So because of this, internal resistance was not negligible, and we had to use the reference charts to find what the convective coefficient would be. And from these charts, it was found that the convective coefficient was 66.67 watts per meter squared Kelvin. And from this, the Biot number was calculated to be 3.33, which is greater than 0.1. And this again confirms that the Heisler charts were the correct method to use. So for the potential pitfalls, there was possibly non-uniform forced convection because the airflow depended on the height of the stand and the position of the cylinder. And the height of the stand needed to be manually adjusted, so it may have not been adjusted to where there would have been most effective airflow over the cylinder. There were also holes in the concrete cylinder, which could have led to uneven forced convection, specifically over the concrete itself. And this may have affected the convective coefficient for concrete. Lastly, there was difficulty in reading the Heisler charts because many of the lines are very close together, and this could have resulted in an H that is bigger or smaller than it should have been.
So an important aspect to consider with this lab is that the heat transfer coefficient is a function of many things. This includes the properties and the flow of the moving fluid, the temperature difference between the fluid and the object, and also the object's geometry. And so subsequently, the value of the coefficient is very specific to the circumstances of the convective heat transfer taking place. So it's usually found empirically rather than theoretically. So the table on this slide displays literature values of the heat transfer coefficients of experiments that most closely mimicked the one that we conducted. And as can be seen, the heat transfer coefficients of the aluminum and concrete cylinders that we found fell between or around these reported values. One trend to point out that supports our coefficients is the fact that for both the lumped capacity method and the Heisler chart correlations, H is indirectly proportional to the size of the object, whether that be the volume of the object or the radius of the object. And so this trend supports our results because the H value of the 69.9 millimeter diameter aluminum cylinder that we used was lower than the reported H values of the cylinders that had smaller diameters. And likewise, for the 76.2 millimeter diameter concrete cylinder, its heat coefficient value fell between the reported values, in which diameters below and above were used compared to ours. Other discrepancies between our values and reported values included different air velocities, as well as unreported temperature differences that weaken comparison. But overall, we believe that these values should still be considered probable estimates for the heat transfer coefficients of these situations. So a key takeaway from this experiment is that the heat transfer coefficient offers insight into how much heat an object must lose or gain for a desired temperature change, or vice versa. So an example would be if you were considering insulating something like a pipe or reactor, You could calculate how much heat the reactor is giving off or taking in from its surroundings to figure out how much insulation would be needed. And beyond the topic of the heat transfer coefficient, forced convection is found in many applications, including in the heating and cooling of materials, which is most notable in heat exchangers, which is found in the figure to the right, and then also in drying processes and chemical reactions.
So in conclusion, for aluminum, aluminum had a smaller internal resistance, a small Biot number, lower heat transfer coefficient of about 45.74, and you could use the lump capacity method. For concrete, it had a larger internal resistance, a large Biot number greater than 0.1. It had a higher heat transfer coefficient of about 66.67, and the lumped capacity method cannot be used for concrete. Altogether, aluminum is great for heat transfer, where concrete is better for insulating. Both cylinders are the same size and shape, however, there is a large difference in the Biot number, and the lumped capacity method could not be used for all materials. For recommendations, it is recommended that more materials are tested to further confirm the lumped capacitance method, further document how materials with low internal resistance are good for heat transfer, and to further document how materials with high internal resistance are good for insulation. It is also recommended that repeat trials are conducted in order to mitigate random error. Finally, some acknowledgements. For this experiment in particular, an acknowledgement is to be made to Tian Li for her guidance on report expectations, as well as Dr. Makas for aiding in the pre-lab portion of this experiment and any questions that arose. A thank you is also to be extended to Dr. Acharya, Dr. Makas, and Dr. Shoep, as well as all of the lab TAs and Mr. Fred Pina for all of their help throughout the semester with each lab and providing us with the guidance to grow and learn about a variety of chemical engineering topics. And here are our references for the experiment.